Welcome to session number 5. In this, we'll discuss the remaining portion of the torsion concepts in the module number 4. So, in the previous session, we have seen some problems, we have worked out some problems, and we calculated how to design the shafts, how to determine the diameter of the shafts for transmitting different powers at a different speed. So in some applications there are some conditions where we may have to replace the shafts with a solid shaft with a hollow shaft or vice versa. So in such cases we have to keep in mind the power transmitted, the speed, torque, angle of twist while designing the new shafts. So based on this replacement of the shafts, we have the problem here where a hollow shaft with inside diameter 60% of its outer diameter has to be replaced with a solid shaft, and the power transmitted should be same and also the speed should be same. So in such case we have to find out the percentage saving in material if you use the same material for both the shafts. So here since the hollow shaft and the solid shaft, in hollow shaft the metal will be saved, but when you want to transmit the same power and same speed, we have to calculate, we have to compare the percentage saving of material in each case. So in the given problem we have a hollow shaft. So here hollow shaft inner diameter is 60% of the outer diameter, and here the condition is that we have to transmit the same power and same speed. So in such case the torque in the solid shaft should be equal to torque in the hollow shaft. So the formula for torque, and we apply the formula for torque with respect to the shear stress and the diameter, polar moment of inertia. So here T torque is expressed in terms of shear stress and polar moment of inertia for the solid shaft, and similarly for hollow shaft we have used the formula, same formula is used with the shear stress and polar moment of inertia for the hollow shaft. So we know these two equations, and we will substitute now, and we will use this condition that torque should be same, the torque transmitted should be same in both the shafts. So using this condition we will use this formula torsion equation with respect to shear stress. So since the metal is same and the shear stress will be same, so in the next step that equation gets simplified, and we will get this equation here. So here, since the internal diameter of the hollow shaft is 0.6 times the external diameter, we will substitute that, and we will get the diameter of the solid shaft D with respect to the outer diameter of the hollow shaft. So if you substitute and simplify the equation, you will get the diameter of the solid shaft will be 0.995 times of the hollow shaft here, outer diameter of the hollow shaft. So you can see here that diameter of the solid shaft is less than the outer diameter of the hollow shaft. So in such case we can find the percentage saving in material. So here if you want to calculate the percentage saving, so we'll take the cross-sectional area of the solid shaft minus the cross-sectional area of the hollow shaft divided by the solid shaft. So we will substitute the area of the cross-sectional area of the hollow shaft, pi d square by 4. So d is nothing but in terms of external diameter of the hollow shaft, and the area of the hollow shaft will be again pi d square, that is external diameter square minus internal diameter square by 4. So this is the standard equations. So we'll substitute that, and we'll multiply it by 100 to get the percentage. So we'll get the 29.8% saving will be there when you replace the hollow shaft with a solid shaft. So similarly, we have one more problem here. So here we have a solid aluminum shaft with 100 centimeter long length and 5 centimeter is the diameter. So it is to be replaced by a tubular shaft of same length and same outside diameter. So we are replacing the solid aluminum shaft with a hollow aluminum shaft, where the outside diameter of the hollow shaft will be same as the diameter of the solid shaft. And here both the shafts should will be subjected to same torque, and also the angle of twist should be same, and over the total length, so length also will be same. So you have to calculate the inner diameter of the tubular steel shaft. So replacing aluminum shaft with a steel shaft here. So aluminum shaft is a solid shaft, whereas the steel shaft is a hollow shaft or a tubular shaft. So since the different materials are used, what happens is the rigidity modulus of these materials will be different. So the solid aluminum shaft will be having rigidity modulus of 2.8 10 to the power of 4 megapascal, whereas the value of G, modulus of rigidity for steel shaft, that is hollow shaft, will be 8.5 10 to the power of 4 megapascal. So you can see that the rigidity modulus of steel is higher than the aluminum. So stiffness of the steel is more than aluminum. So we'll take the solid shaft first separately. It's made up of aluminum. So if it is made up of aluminum, the rigidity modulus will be different for the aluminum shaft. So it is GA or CA here, and length will be same, 100,000 millimeter. So it is 100 centimeter. So it is, we take it as in millimeters, 1000 millimeter. Diameter is given as 5 centimeter or 50 mm. So here, for case of hollow shaft which is made up of steel, the rigidity modulus GS or CS will be different as given here, and the internal diameter is DI, external diameter is DE. So DE is told that external diameter of the steel hollow shaft is equal to the diameter of the solid shaft, so it is 50. So DE is taken as 50 mm. So you have to calculate the value of internal diameter of the hollow shaft. So here again the torque will be same for both the shafts. So this is a condition of compatibility. So the torque transmitted by the torque induced in the solid shaft should be equal to the torque exhibited by the hollow shaft. So we put the same formula. So here we are not using the strength consideration, but we are taking the stiffness consideration, because the value of rigidity modulus is given and angle of twist is mentioned as same with the length. So we take T by J is equal to G theta by L, the stiffness part of the equation, torsion equation. So now it is simple now. So J is nothing but it is for the polar moment of inertia of the two shafts had to be considered here. So when you take the torque of solid shaft and hollow shaft, we equate that, and if we modify this equation, torque is equal to J into G into theta by L. So this we equate for both the shafts. Since torque is same, so it will be written like this. So for solid shaft it is torque here, for hollow shaft this is the torque. So see here G value will be different, theta will be same, length will be same, and polar modulus it will be different. We have to calculate that for hollow shaft and solid shaft. So if you cancel this L and L will be get cancelled, theta and theta will get cancelled, so remaining will be J into G. So G into J or J into G. So this is the torsional rigidity. So G into J, the product of rigidity modulus and the polar modulus, polar moment of inertia, is called as torsional rigidity. So G into J is called as torsional rigidity. So now this rigidity, torsional rigidity of solid shaft will be equal to torsional rigidity of the hollow shaft. So now the equation is simplified here. It is simplified like this with the formulas for J. So polar modulus of the solid shaft will be pi d to the power 4 by 32, and this is the rigidity modulus of the aluminum solid shaft. And similarly the polar modulus for hollow shaft will be, the formula is, you know that, and again this is the rigidity modulus of the steel. So the Ca and Cs, that is rigidity modulus of aluminum and steel, we know, substitute that, and the diameter of the solid shaft is known, and the inner diameter of the solid shaft, external diameter of the solid shaft is known, that is same as d here. So keep all the values with same uniform units, and if you substitute that, you can get the value of d. So we'll get the value of d in millimeters, because all the other units are in millimeters. So we'll get the value of d in millimeters here. So internal diameter of the shaft will be 45 millimeter. So basically in all the problems you can see that the torsion equation is, it's only one equation, and accordingly we manipulate, or we just readjust the equations to get the unknown value. So if you remember the torsion equation and the power equation 2 pi nt, we can solve, or we can design any shaft for different applications with different conditions of torque, or maybe angle of twist, length, diameter, or other parameters which are involved in the torsion equation. So we have one more problem here with a solid shaft of 20 centimeter diameter, it's having the same cross-sectional area as that of the hollow shaft. So here the cross-sectional area of the hollow shaft is same as the cross-sectional area of the solid shaft. So instead of giving diameters, he is telling the area is same. So you can calculate the diameters easily. And also inside diameter of the hollow shaft is given, so you can easily calculate the outside diameter of the hollow shaft, because the area is same. So we have to find out the ratio of power transmitted by the two shafts. So here we have to calculate the power transmitted by the two shafts, and we can take the ratio of those two. And also he is asking you to compare the angle of twist over the length of these shafts when the stress intensity is same and the shear stress will be same. So here since the area is cross-sectional area of the hollow shaft is same as the solid shaft, we first will take that condition. So if you substitute the formulas and if you substitute the values, we can easily get the outer diameter of the hollow shaft. So you can see here, this is the area of the solid shaft d, diameter d, and this is the area of the hollow shaft with outer and inner diameters. So this should be d square and d square and di square. It is wrong here. So it is d square and d square here. So if you simplify that and calculate that, you will get 250 millimeters. So directly we can, so once we know the diameters or the values of diameters or the parameters related to the power. So in power equation is 2 pi nt by 60. We know that it is same for both the shafts. The equation will be same. So you can take the ratio of hollow shaft to the ratio of solid shaft. So ratio of power of the hollow shaft to the power of solid shaft is taken here. So 2 pi nt, the formula is same for both the shafts, hollow and solid shaft. So since the power RPM is same, the same speed is taken, so we are left with only the torque of the hollow shaft and the torque of the solid shaft. So here the torque of the hollow shaft and solid shaft will be different because same speed is transmitted. So you can take the ratio of this. So we'll take the ratio of these two torques. We can find out, we can relate the torque with diameters, and we can get the values here. So since the torque formula is related to the shear stress with the torsion equation, T by J is equal to tau by R, so that equation we can take here for hollow shaft, and J is different here for hollow shaft and the solid shaft, so they are in terms of the diameter. So since all the diameters are known and since the shear stress is same, so this equation will be simplified. You will get it down to only the diameters here. So the ratio of powers of the hollow shaft and the solid shaft is in terms of the diameters which are known to us. So if you substitute that values, we can easily get the ratio here. You can see that the power transmitted by the hollow shaft is 1.7 times power transmitted by the solid shaft. So the power transmitted by hollow shaft is 70% more than the solid shaft. This observation we can make here. And again we can calculate the angle of twist of the two shafts. So here we will take the ratio of the angle of twist. So this equation, torsion equation with respect to stiffness, or since the shear stress is same, we'll take the second part of the equation with respect to shear stress and the angle of twist. So here we are not considering the torque. You can consider the torque also, T by J with respect to angle, or you can consider the shear stress with respect to the angle of twist. So you can take any part of the equation depending on your analysis and on the given data. We try to simplify that equation. So here now we will take the angle of twist on one side and we will readjust the factors, other factors here like this. So here this is the angle of twist for the shafts. So now we will take so in case of this is given in terms of radius here. So it is R is the radius of the shafts here. So theta h, that is first we will take the hollow shaft. When you take the hollow shaft, so this formula will become shear stress of the hollow shaft, length of the hollow shaft, the rigidity modulus of the hollow shaft. Since the metal is same, G and G for hollow shaft and solid shaft will be same, and R will be the radius of the that is of the solid shaft here. So this is hollow shaft here, so we will take the radius as the outer radius of the hollow shaft here. Similarly for solid shaft the formula remains same, so here it is the radius of the solid shaft R. So since if you take the ratio of these two now, that is we will take the ratio of hollow shaft to the solid shaft with respect to the angle of twist. So here since shear stress is same, it will get nullified, and since the rigidity modulus is same, it's a metal is same, C and C, that is G and G will be same. So we are left with and also length is same, so we are left with only RE and R. So if you simplify this, okay, this denominator will come to the numerator here, R by RE. So we will get this ratio here with respect to the radius or the radii of the shafts. So the angle of twist ratio for both the shafts is now in terms of the radii of the shafts. So here R is the radius of the solid shaft, RE is the outer diameter of the hollow shaft. So since both are known, diameters are known, or you can take it in terms of radius. So R is equal to D by 2. So you can take the values, diameters are, we know that, so you get the ratio as 0.8 here. So here again one more thing you can observe here is that uh, the twist angle of twist or stiffness of the hollow shaft is 0.8 times of the solid solid shaft in this case. So here one more problem is there, where the polar modulus is same for both the things. The polar modulus is nothing but it is J polar moment of inertia divided by the radius of the shaft. So it is J by R. So J by R is taken as the polar modulus or Z in case of the shafts here. So ZP is called as polar modulus. ZP is called as polar modulus. H is for hollow. So Z is nothing but J, that is Z is polar modulus is equal to polar moment of inertia J by R. So R is taken with respect to the outer diameter of the shaft here. So here we have a steel shaft again. It's a hollow shaft uh, with external and internal diameters are given here, and we have to replace that steel shaft by a solid alloy. So if the metal is different here, so hollow shaft is made up of steel and the solid shaft is some other alloy shaft, some other alloy. So so what happens is the rigidity modulus will be different for both the shafts because different materials are used. So that steel rigidity modulus for steel is given as 2.4 C for alloy. So the ratio is given in terms of uh, rigidity modulus. So rigidity modulus of steel is 2.4 times of the rigidity modulus of the alloy. So here we have to calculate the diameter of the solid shaft, which is replacing the hollow shaft here. And also we have to find the ratio of their torsional rigidities. So I told you that G into J is torsional rigidity. So the product of modulus of rigidity and the polar moment of inertia G into J is called as torsional rigidity in this case. So again the formula remains same, it's a torsion equation only. With that equation only we have to do whatever problem is asked here. So you have to satisfy all the conditions in the problem, that's all. So the main equation is torsion equation only, one equation you have to remember, and based on that only, depending on the problem you have to readjust the equation and get the unknown value. So here you can see in the diagram, this is hollow shaft steel and this is alloy made up of some alloy. This is a solid shaft with diameter D. So we have to find out the diameter of this solid shaft, as well as you have to find out the ratio of the torsional rigidities of both the shafts. So here first thing is polar modulus he has mentioned, it is same. So we will calculate the polar modulus of the hollow shaft first here. So I told you that polar modulus is nothing but ZP. The polar modulus is nothing but J by R. So J is pi d to the power 4 minus di to the power 4 by 32 dE. So again R is nothing but dE by 2. So if you do that, you will get this as pi by 16 d to the power 4 minus di to the power 4 by dE. So R is dE by 2. Radius of the hollow shaft will be outer diameter by 2. So this 32 and 2 will get cancelled, that is 32 divided by 2 will get 16 here, the remaining remains as it is here. So since the diameters are known, you substitute that value, you will get the polar modulus in terms of millimeter cube, because it is due to the power of 4 here and here it is D here. So one power will be reduced here, so it is millimeter cube. So polar modulus will be in millimeter cube, so it represents the volume of the material. So similarly we'll calculate the polar modulus of the solid alloy shaft. So here again the polar modulus is in terms of the diameter, we know that. So again polar modulus is nothing but J by R. So by d to the power 4 by 32 divided by d by 2. So you'll get this pi d cube by 16. So this is the polar modulus of the alloy or the solid shaft here. So the condition is that polar modulus should be same for solid and hollow shafts. So we'll equate these two equations now. So pi d cube by 16, and this is the polar modulus of the hollow shaft which is known. So in this polar modulus of the solid shaft diameter is not known. So by equating this equation we will get directly the diameter of the shaft. So it is 278 millimeters here. So again you should be careful with the units. So keep these values in millimeters. Okay, we will get the diameter in millimeters only. If you keep in meters all the values, then diameter will be in meters. So next, coming to torsional rigidity, I told you that it is nothing but G into J or C into IP here. So C is nothing but rigidity modulus G here, J is nothing but polar moment of inertia IP here. So if you take the ratio of those two, that is G into J for the solid shaft and G into J for the this is for the hollow shaft and this is for the solid shaft. So just to compare the G value, G of the solid shaft is compared with the G of the alloy shaft here. So rigidity modulus of the steel shaft is compared with the rigidity modulus of the alloy shaft, and we know that rigidity modulus of the steel is 2.4 times the rigidity modulus of the alloy here. So in this formula you just substitute Cg, that is Cs, that is the rigidity modulus of steel, as 2.4 Ca or Ga. So this will get Ga will get cancelled here, and polar modulus of the hollow shaft is known, diameters are known, and similarly polar modulus of the solid shaft diameter is known. Substitute the values and you will get 2.59 as the ratio. It's very simple. These problems are very simple. Only thing you have to remember the torsion equation, and depending on the conditions of the problem, just modify the equations and get the unknown values. So here we have one more problem where he is asking you to calculate or compare the weights of the solid shaft with that of the hollow shaft, which is made up of the same material and same length, to transmit a particular horsepower with a given speed and also the maximum shear stress. And here he is telling you that inside diameter of the hollow shaft will be 0.8 times of the outside diameter. So here we have the diameter of the solid shaft, we take it as D, external diameter of the hollow shaft will take it as DE, internal diameter will take it as DI. So DI is 0.8 times DE, so that relationship is given here. So here weight of the material or weight of any material is taken with respect to the density of the material. So if you take the weight density of the material, so different materials will have different weight densities. So the formula is weight density is nothing but weight by volume. So area into length is volume. So if you take the density is nothing but weight by volume. So if you take mass density, it is mass by volume. If you take weight density, it is weight by volume. So you want the weight here, so weight is nothing but volume into weight density. So this density is again a property of the material, so it is different for different materials. So in this case, since it is same material, density will be same for both the hollow shaft and the solid shaft. So if you take if the material is same, densities will be same, but the weight will be different for hollow and the solid shaft. So here directly we'll take the ratio of the solid shaft and the hollow shaft here with respect to weight. So here weight, I told you that weight is nothing but volume into weight density. So we'll take the area, length and density of the solid shaft, area, length, density of the hollow shaft here. So the cross-sectional area of the solid shaft will be different and the hollow shaft will be different. Length anyway it is told that it is same, so this will get cancelled. So density of the since the metal is same, density of the hollow shaft and the solid shaft will be same, so it will get cancelled. So what we are remaining with only the areas of the solid shaft and the hollow shaft. So here we are expressing the weights of the solid and hollow shaft with respect to the areas of those shafts, corresponding shafts. It is directly proportional. You can see here weight of the solid shaft is directly proportional to the area of the solid shaft by reducing this, by simplifying this equation. So now we know the weights here with respect to the area. So since the diameters are known, directly I will go to the area of the solid shaft, pi d square by 4, and area of the hollow shaft, we substitute that, we will get 2.78 d by d square. This is the ratio of the outer diameter of the diameter of the solid shaft and outer diameter of the hollow shaft. So since the torque is same, we don't know the values of the diameters. So now we will take one more condition, that torques are same for both the shafts here. So torque will be same. So again we go to torsion equation and we express the torque in terms of shear stress and the diameters. So since the metal is same, the shear stress will be same here for both the hollow shaft and the solid shaft. So what happens is, now we are getting the ratio of one more equation which expresses the ratio of d and de. So if you simplify this equation, since the metal is same, shear strength intensity also will be same. So we can express the value of d in terms of de. So if you take these two equations, we get d by de 0.839. So now we have two equations which relate d and de. So this is the second equation which relates d and de, and in the previous case we have this equation which relates d and de. D by d ratio is there. So in the second equation I got the ratio d by de. So substitute this value in this equation, so that I will get the ratio of weights. So when substitute the d by d ratio in this weight equation number 1, so I will get the weight ratio as 1.96. So you can see here weight of the solid shaft is 1.96 times the weight of the hollow shaft. So for the same material, for the same torque and the same power transmitted, the solid shaft, weight of the solid shaft will be 96% more than the hollow shaft. So this you have to observe here. Obviously the weight of the solid shaft will be more than the hollow shaft for the same torque transmitted. You can see that it is very high. The weight is almost double of the hollow shaft for the same properties, for the same functioning of the shaft. We have one more problem here with power. 2.2 megawatt has to be transmitted at 60 rpm. So megawatt is 10 power of 6 watt, and if the allowable stress in the material is given here, so this is the shear stress 85 megapascal, and you have to find out the diameter of the shaft if it is solid. And one more condition is that if you use a hollow shaft with diameters, you have to calculate the percentage saving in weight, and density of the metal of the shaft is given here. So here one more thing you have to see here, that the material is same. So you not mentioned about different materials. The material is same for hollow and solid shaft. So obviously density will be same for both the shafts. Yes, given the density of the metal also, the value is given. So since we take the ratios, this is not required, density may not be required. So here coming to the power here, so whenever power is given, you can calculate the torque by this equation. So power is given and the RPM is given, directly we will calculate the torque which is transmitted in the shaft here. So first we'll calculate the torque directly by this formula. So the power is given in terms of megawatt. You can take it in, you'll get it in Newton meter. So if you put the values of N 60 RPM, torque you will get it in Newton meter or kilonewton meter. So yes, convert that into millimeters to keep the uniform units. So once you know the torque, we'll come to the torsion equation, and the diameter of the shaft we can find out by using this torsion equation for strength, that is tau, shear stress here, tau here, Fs. So torque is nothing, T by J is equal to tau by R. So if you simplify that, you will get the torque in terms of the shear stress and the diameter. So diameter is unknown, we have to calculate that. Torque, you just know, we found out this. The shear stress is given here, yes. So the shear stress of the material is given, shear strength of the material is given, allowable shear stress in the material is given as 85 megapascal. So this is in megapascal, you have to convert that into Newton per millimeter square. So you should be careful here while substituting the values of this 85 megapascal. So 85 megapascal is 85 in 10 to the power of 6 Newton per meter square, or 85 into 85 Newton per millimeter square. So that conversion you have to keep in mind, and while substituting that you should be careful here. So 85 in 10 to the power of 6 Newton per millimeter square. So it is 85 Newton per millimeter square. Megapascal is 85 megapascal is 85 Newton per millimeter square. So directly is given 85, and torque is given in Newton millimeter only. So just now we found out that. So we substitute that, and we'll get the value of cube root d in terms of cube root of the torque here. So we'll get the value of the diameter of the shaft. It's very simple. Just remember the power equation. Just remember the torsion equation with respect to the shear stress and diameter. So coming to the hollow shaft again, so here again the torque transmitted will be same from the solid shaft to the with respect to hollow shaft. So using that concept, Ts is equal to Th. So Ts just now we found out that. So that you will be equating with the torque of the hollow shaft. So here we'll get an equation with respect to dE and dI. So dE and dI, your diameter we just found out now for the solid shaft. dE and dI, the diameters, the relationship is mentioned here for the hollow shaft here. So dE is 4 by 3 times of dI, or dI is 3/4 times of the dE. Using this relationship, we substitute that here, and we will get the value of dE first. So and dI is 0.75 times of the dE. So we'll get the value of dI here. So once we know the diameters of the shafts, we can calculate the cross-sectional areas of the material, and we know that in the previous example, weight of the materials, weight of the shafts is is expressed in terms of the cross-sectional areas of that shafts here. So using that we can calculate the areas of the cross-sectional areas of the shafts, hollow and solid shafts here. So once we calculate the diameters, now we will go to the percentage saving in material with respect to weight here. So percentage saving in material is nothing but in terms of weight, we take the ratios weight of the solid by hollow. So that is nothing but you know that it is directly related to the area of the solid shaft. So percentage saving is weight of the solid shaft minus weight of the hollow shaft divided by weight of the hollow shaft. So here we are taking weight of the solid shaft with respect to hollow shaft here. So we are dividing it by the hollow shaft. So percentage saving will be 43% when you use the hollow shaft here. So once we know the diameters, we can easily calculate the areas of the shafts. The percentage saving in material with respect to weight is given with respect to the areas. So weight of the solid shaft minus weight of the hollow shaft by weight of the solid shaft is there. So these weights are related to the areas of the solid shaft and the hollow shaft. So we can take the solid shaft area here, the hollow shaft area divided by the solid shaft here. The percentage saving material is 43%. So if you use the hollow shaft, you can save 43% weight of the material is saved here. This should be weight of the solid shaft here. So we can prove some theory here that the hollow shaft is stronger and stiffer than the solid shaft when you use the same material having same length and weight. So here for strength, for strong or for strength, we use the torque here. So the torque of the hollow shaft, the ratio is taken with respect to the solid shaft here. So here it is saying that it is same weight. So since the weight is same, it will be stronger. The solid shaft will be, the hollow shaft will be stronger here. So since the weights are same, we take the area, density and length as same. So since the metal is same, density will get cancelled, length is same will get cancelled, and we will get the ratio of these diameters for the hollow and the solid shafts here. So in this case, d square will be equal to d square minus di square. So this equation, this relationship, we will use it here when you take the ratio of the torques of the hollow shaft and the solid shaft here. The metal is same, so if you want to prove it is stronger, we will take the hollow shafts with respect to the shear strength here. So the torque is expressed in terms of by using the torsion equation. Torque of the two shafts is expressed in terms of the shear stress. So shear stress will be same. So since the metal is same, the strength will be same, and we will get the torque in terms of the diameters. So using this relationship, we substitute the values here, and if you do the calculation here, if you simplify that, we will get that the torque in the hollow shaft is greater than torque in the solid shaft. So here we don't have the values here, so you can just compare, you can just analyze that the ratio will be greater than 1. So this ratio cannot be less than 1 here. So since these values, if you take any values and if you just assume some values for these two, this ratio will be greater than 1. So since the ratio of the torque of the hollow shaft is greater than the ratio of the solid shaft, we can say that the hollow shaft is torque is greater than the solid shaft, because the ratio is greater than 1. So we can say that the hollow shaft is stronger than the solid shaft for the same material and weight. So similarly, we can prove that the hollow shaft is stiffer, which is having more stiffness than the solid shaft here. The stiffness, I told you that angle of twist is a measure of stiffness in case of torsion. So we will take again, so we'll take the equation, torsion equation, T by J is equal to G theta by L. So we'll take the stiffness here as T by theta is taken as the stiffness. So if we take that T by theta, and if we substitute the values of both the hollow and the solid shafts with respect to the diameters, and if we simplify that again, we will get that T by theta is greater than 1. The ratio of stiffness of the hollow shaft is greater than the solid shaft here, since the ratios of the stiffness is greater than 1. So we can say that hollow shaft stiffness is more than the solid shaft here for the same material having same weight. So if we take the same material with same weights, so hollow shaft is stronger and stiffer than the solid shaft. So by observing the previous problems, we can answer this question that why the hollow shaft is preferred than the solid shaft here. So we know that hollow shaft will be lighter in case will be lighter than the solid shaft, and the cost of the material will be less for the same torque developed here, and the strength is better in hollow shaft than the solid shaft. And if you take the same weight, the hollow shaft is better than the solid shaft. Just now we proved that the strength and stiffness is better in case of hollow shaft than the solid shaft for the same weight. So we prefer the hollow shafts while designing the shafts for critical applications. That's it for this session now. Thank you. In the next session, we'll look at some more concepts of the torsion.